In this video lecture, we're going to be talking about how to create functional programs. There's not any good notes I can point you to for this lecture, as it's more a demonstration of the way that you can go about creating functional programs. And we're just going to work through three different examples, one with Factorial, one with summing a list, and one with quicksort. So we're going to be moving through a progression of increasingly difficult problems. And there's essentially two ways that you can create a functional program. One is using tail recursion, and if you remember from previous video lectures, that typically involves or may involve using continuation arguments because you may have to pass some intermediate results into the next invocation of the function. And I think of tail recursion as being akin to pre-processing a list, meaning you do whatever processing you have to do at the beginning, and then any further processing gets passed to a future invocation. And you'll see more what I mean by this in a moment. The second way you can construct a functional program is using what I would call inductive construction. And this is basically going from the way you might inductively define a function, and is more akin to post-processing a list because the inductive approach is going to essentially start with the case where we say n equals 0, the base case. And then we're going to assume we have something that works for the case of n, and now we're looking to extend it to n plus 1 elements. And we'll assume we have the solution to the n element case, and we will do additional processing to extend the solution to the n plus 1 element case. And so I say that this is like post-processing a list because we're going to assume that we have a solution to the final n elements of the list, and then when we're done with that, we will do the first element and add it into the result. So either of these two ways is a fine way, and you should use either way in your homework assignments unless I explicitly tell you to use tail recursion or the inductive construction approach. So now we're going to just work through a few examples starting with Factorial. So I'm showing the inductive construction first, and if you remember that Factorial is simply if n is 0 or n is 1, we return 1, and otherwise it is n times the result of evaluating the factorial on n minus 1. So this definition you see for scheme just follows this inductive definition of Factorial. In particular, you can see I first get the solution for the n minus 1 case. Once I have that result, I multiply it by n to get the actual factorial. Now compare that with the tail recursion version, where we're going to start by doing the product first and passing it down. And it will, in general, the tail recursion versions are going to look more complicated. So in green, I have highlighted the helper function that we're going to need for this tail recursion. And whenever you need continuation arguments, you're typically going to have to have some kind of helper function. So let's look at the helper function first, and then we'll look at the overall function. So with the helper function, what we're doing is we are always passing in the product that we have seen thus far and the current value of n. So now when we get down to the final cases where n is 0 or n is 1, we assume we've already built up the product, and so we return the product. You may contrast this with the previous approach where the inductive case returned 1. Now we assume we have the ultimate result and we're simply passing it back. If we're not yet to that point, you'll see that what we do is we are building up our product by multiplying n by the product we have thus far. and we are decrementing this argument by 1. So it's like we're saying for I equals n down to 1, product equals n times I. And this is more like the imperative approach. This is more akin to pre-processing because you can see that there's never any computation done after we return from fact helper. We're simply returning the results. The pre-processing is right here where we say times n product. We're doing the multiplication on the front end prior to calling the recursion, whereas in the inductive case, you can see we did the multiplication after calling the function. So that's why I said inductive construction is like post-processing and tail recursion is like pre-processing. Now, when we call factorial, we don't want to have to call it with the continuation argument. That little piece of implementation should be hidden from the user. They should only have to pass in the value of n they want factorial calculated for. So after our definition of fact helper, we call it with n and with 1 as the product so that it can start building up. So in this case, we have provided the base case as the product thus far. Also notice I had to use letrec here because I'm using a recursive function or defining a recursive function fact helper. And if I just used a let, you would get an error message from the scheme compiler. Let's move to our second example now where we're summing up a set of numbers. So let's actually, before doing anything else, I'm going to show you an example of what this is doing and how you would invoke it. So the way I would invoke this is just give it a list like 5, 6, 10, 15. And what I'm doing is I'm summing it up. And if you just quickly do the sum in your head, you should see it's 36. This is summing a list of numbers. And again, we'll go with the inductive construction first. So the base case I'm going to assume is where we have a null list. And I'm assuming that's not an error. Instead, I'm assuming a null list will just return a value of 0. So then if you think inductively, if I already have the solution to an n element list, the way I get the solution to an n plus 1 element list is to simply add the n plus first element to the sum I had for the first n elements. And that's what this case right here is doing. It's saying by default, we are first going to sum the tail of the list, i.e. the remaining n elements, and once we have that sum, we're adding to it, in effect, the n plus first element, which is the head of the list, the car, and we're just returning that sum. So that's a very simple construction, or a simple looking function. And again, you see the tail recursion construction looks more complicated, and again, because we're using a continuation argument, we have to define a helper function, which again I have highlighted in green. And again, we'll discuss it first. So we are summing a list, and so what we're going to be doing now is starting from the front of the list, and we're going to be keeping a running sum from the front of the list. And that's going to be the sum thus far. So again, our base case is when we've exhausted the list, we need to return. And in this case, we just return the sum that we've computed. Otherwise, we still have another element. And what we're going to do is add our first element of the list to the sum that we've accumulated thus far. And then we are going to be repeating the computation on the rest of the list. So again, notice the pre-processing element to this tail recursion, which is that before we call it recursively, we are adding in the sum. We're doing the productive work of this invocation before calling the recursive version. Whereas if you look again at the inductive construction, we first called the recursive version, and then after it returned, we did our addition, hence post-processing. And again, we're hiding the helper function from the user, so we just have the user pass in a list, but we immediately call our helper function passing in the list and our base value of 0. And either way is going to work. It's just, again, a bit of a matter of preference. It's also, if you remember from previous lectures, tail recursion allows the compiler to do optimizations it might not be able to do with non-tail recursive functions. In particular, it can reuse the stack frame and avoid the recursive calls. It can just basically use a goto statement and make it look like iteration. So the tail recursive version is likely to be more efficient. Now, also before I move on, just a word about testing your functions, because you'll often have errors. What I suggest doing is first testing the base case, which in this case is the empty list. Aha, it works. It returns 0. So then try it with the next simplest construction you can have, which is going to be a one-element list. And again, aha, it works. And then maybe build that up so it's a two-element list. And once that works, then you might just start experimenting with some bigger lists and making sure that it works for them as well. Another thing that you should just be aware of is you want to write your functions a little bit at a time, because the Lisp interpreter, or I'm sorry, the scheme interpreter is not particularly good at giving error messages. Okay, so here's one simple error. I'm putting an extra parentheses here next to the lambda, and I will take one away from here because you can see they're now matched, and I will put this in here, and you see it just says ill-formed special form define sum list lambda let rec to continue call restart. So you really don't have any good idea where the problem is, especially as you can see it's saying lambda ... let rec ... and it's not at all clear that what you had here was the missing parentheses. So you're just going to have to write your functions a little bit at a time, test them, and just put up with the fact that you're not going to get really good error messages from the scheme interpreter. Let's move on to the last and most complicated example with quicksort. And we're going to again go with the inductive construction first and then the tail recursive version. And it's going to turn out that it's only the partition step of quicksort where we worry about the inductive or the tail recursive version. So if you remember, the kind of core element of quicksort is you have a pivot element and you take all elements less than the pivot and put it into one list, and you take all the elements greater than the pivot and put it into another list. And you keep breaking down these lists until you're down essentially to just a list with either 0 or 1 elements, at which point you have a sorted list. If you need to review quicksort, you should take a moment and review it. I'm just going to show you what the result of partition should look like. I'm just going to take one of these lists or one of these definitions of qsort partition and going to give it a pivot of 10 and then just an arbitrary list of elements and run it, and you can see that what I have returned, I've returned two lists. The first one is all the elements less than 10, and the second list here is all the elements greater than 10. And you may wonder why this second list isn't parenthesized, and it's just the way schema shows what looks like a list. This is actually, I tried to return it as a cons of two lists, but scheme is the first element of the cons is a list. The second element is also a list, but it's going to show that second thing is just a list of items, not as you would expect as two lists with parentheses around them. So you just got to get used to this kind of odd way sometimes of scheme showing you a pair of lists. So moving back to the inductive construction, we take in our inductive version, we get a pivot and we get the list. And if the list is null, that's our base case. We've gotten to an empty list and we just return a pair of empty lists. So remember, the first list is going to be all elements less than the pivot. The second list is going to be all elements greater than or equal to the pivot. So in the inductive case, we're going to first get the n element solution, which means that we're going to first partition the last, say, n elements of the list using the coulter, and we'll put that into result. And then I'm returning a cons pair, you can see. So the car will give me the list of elements less than the pivot, and the coulter of that result will give me the list of elements greater than or equal to the pivot. And you'll notice here I'm using a let star. A let star says to evaluate the elements in the let sequentially, that is the name value bindings. If I didn't do that, then scheme could evaluate them in any arbitrary order. And it should be clear, we don't want to do these car and coulters until we have the result. And that's what let star does, is it forces scheme to evaluate them in sequential order. There could be advantages to not having to do it in sequential order. One obvious thing is parallelization. If they don't depend on each other, I could put these computations on separate cores and perhaps speed up the computation. Okay, so once I have separated the end of my list or tail of my list into a lesser and greater list, now I'm just going to prepend the head of the list to whichever list it belongs to. So if the first element of my list is less than the pivot, then I add it to the lesser list. And I do that by consing that first element to the lesser list, and then I'm returning the cons of the lesser list and the greater list. And similarly, if the element is greater than or equal to the pivot, then I prepend it to the greater list, and again I return the cons of the lesser and the greater list. So again, I am doing post-processing because I first get the result of partitioning, in effect, the n element list, and then I'm adding the first element to that, the n plus first element, down here. So pre-processing. Okay, so the tail recursion version, in this case, we don't need, our helper function actually is qsort partition. So in this case, we have just changed the number of arguments so that there's 4 arguments rather than 2, and we are now going to be building up our lesser and greater lists, which are L1 and L2, as we go along. So as we come to each element in the list, we immediately assign it to either L1 or L2, the lesser list or the greater list. And when we're done, we're simply going to return the 2 lists. So here's that thing. If the list is null, we've exhausted its elements, we simply return the pair L1 and L2, where L1 is the lesser list and L2 is the greater list. Otherwise, we're going to use a let to get the first element. And here I don't need to use the let. I could always replace first element with car of L, but it makes the code a little more readable. So we're asking, is the first element less than the pivot? If it is, you can see we add it to the lesser list, L1, and we then call our QSort partition with the remaining part of the list and the newly augmented lesser list and the original greater list. If we're supposed to instead add the element to the greater list, we do that. We prepend it to the greater list, and we then call our QSort partition on the rest of the list, passing it the original lesser list and this augmented second list. Now, if I do the second definition, you're going to, this tail recursive definition, you're going to see that there's actually the two lists will get, the original list will get partitioned correctly, but you'll see the elements aren't in the same order as with the inductive version. So in this case, there is a bit of a change to the result. So this is, let's put here the tail recursive version. Make sure we call it, we have to give it two empty lists. Okay, so you see it's 651235, and this one was up here 532156. So they're in a different order. They've still been partitioned correctly. It's just the order is different because with the inductive version, we waited to the very end to put this 6 here, whereas here we did it immediately. In fact, if you look at them, they're going to be reversed. This is 651,235. I read this from the reverse, 651,235. So it's just the reason we have the different results is in one case we were waiting to the end and then prepending, and in the other case we were doing it at the beginning and prepending. So it's simply mirror images of each other, but since there's no side effects, we still have the right partition. Okay, and finally, let's just look at the actual quicksort itself. And all the quicksort has to do is check to see if the list is null. We're simply going to return the list. Otherwise, we're going to first partition. In this case, we're using the tail recursion version because we're passing 4 arguments. And the pivot is the first element of the list, and then we partition the remaining part of the list, and that's what's going to come back in these 2 lists. So that's why when we're done, our result is in lesser list and greater list. And again, notice we're using the let star so that we force the evaluation order. And now we simply create a list with 3 parts. We QSort the lesser list, stick the pivot in the middle because it's between the lesser and greater list, and then we quicksort the greater list. And when we're done, we have a sorted list. And if we're using the inductive version of QSort partition, the only difference is that we would get rid of these last 2 arguments like that. That would be the only difference. So hopefully this video lecture has given you an idea of 2 types of ways to create functions. Again, one using tail recursion by using continuation arguments and pre-processing the list, and inductive construction, which is typically the more natural way, in my opinion, to write your functions because it's based on the actual inductive definition that you're actually given often of a function, and it's akin to post-processing because you're assuming that we first have the n element solution and then we're adding the n plus first element in somehow, thus post-processing the list. And the tail recursive version typically is more efficient because the compiler can optimize it by reusing the stack frame and not making function calls. The inductive construction, as we've seen, often leads to cleaner, more elegant code. Again, for this course, which technique you use is up to you unless I specifically tell you to use one approach or the other.